Now that you've gotten to explore LLVM a bit, the next step is to walk through creating a really boring pass. It's going to be your job, your task for this lesson, to make the pass do something interesting. If we return to the tutorial that we're following, there's a recommendation that we clone this starter repository. And I really recommend that you do this, that is, follow the starter repository instead of starting from scratch, just because the build system is kind of annoying to set up. You have to set up all these CMake variables to make stuff work. Anyway, let's check out what's here in this pass before we move on. There's a skeleton directory that contains the code. All the actual code is in this thing called skeleton.cpp. And if we open this up, you can see that it's a pretty short file. The pass is just a subclass of function pass, which you can find in the LLVM documentation. And the main thing that it has is this runOnFunction method. This takes a function object, an LLVM function object that represents that thing like main, like we saw in the previous video, and we will do something with it. At the moment, we're going to do the dumbest possible thing, which is just to print out the name and move on. This thing that returns false indicates whether we change the function. In this case, we are just reading the function, so we return false. Eventually, we're going to be modifying the function on the fly during the pass, and we will need to return true from this method. In any case, let's compile and run this method. Oh, one more thing. There's also this errors thing, which you can think of it as like roughly similar to like cout or carr from like the C++ standard library. Anyway, errors is a special C++ output stream that you can use to print out debugging information. It's in the LLVM namespace. I have done using namespace, so that's the same as just doing explicitly using errors from the LLVM namespace with the double colon thing. All right, so let's build this. So inside here, the way to build this is that with this, as is standard with using CMake, you got to make yourself a build directory, and then you go in there. And then we have to do a CMake and then tell where the stuff is that we want to build. On a lot of systems, including like the macOS where LLVM is installed from Homebrew, you need to tell CMake where your LLVM installation is. And you can do that with the LLVM dir environment variable. So for me and for Homebrew in general, LLVM is located here. There is inside the LLVM installation, you need to have this like CMake directory, LLVM. In any case, you need to tell CMake that this is where the CMake files are for LLVM itself. Okay, then we need to do that command. So CMake ... And that will generate the build files for us. Then next, we just have to type make to actually build our pass. This will build a thing. Under this build directory, there'll be a directory called skeleton where the build products are. And libskeletonpass.so or something similar like this is the output of the build process. So it's a shared object that is a dynamically linked library that will be loaded into LLVM to actually use it to do stuff. Now let's actually run that pass. So I'll go back up to this directory and I'm going to make a file to build. I'll just call it main a.c again. I'll just make this even simpler. I'll just return 42 from this thing. Anyway, I will want to compile this while running our pass on it. The way we do this is we run clang, and we have to make sure now, if you are not sure, check that you are using clang from the same LLVM installation that you just built your pass against. So the same thing from that LLVM dir that we just used. We need a few magic incantations to actually use our pass. And this is what you do. You do xclang load, xclang. I know this looks weird, but now you have to give the path to the shared library that we just built. So that's in build skeleton and then libskeletonpass, and on my machine it's .so. Then we have to give it the file that we want to run it on. And this indeed compiles the file. In fact, it just does a normal thing. It creates a.out as Clang does in its default configuration, while also running our pass on the code as it goes by. So we get to see the output from this output statement that just like prints out the name of the function. And congratulations, if you've done this, you have compiled and run your very first LLVM pass. Let's now look a little more closely at the LLVM intermediate representation. The programs that you get to manipulate as a pass in LLVM are just C++ objects, like function that we already saw. Now I'm going to show you a piece of the blog post that has this diagram that illustrates some of the most important objects, that is C++ classes, that you're going to have to deal with when manipulating programs as an LLVM pass. First, there's module. Module is you can think of it as roughly corresponding to like an original C source file that got compiled with Clang. but roughly it's kind of this container that contains everything that will eventually be translated into an object file. So this includes functions and globals and other stuff like that. I want to emphasize that everything I'm going to be talking about is just a C++ class that you can find documented in that big Doxygen reference that I referred to in the previous video. The most important thing that modules contain are functions like main that we saw in that little snippet of LLVM earlier. They in turn contain basic blocks, and those in turn contain instructions. In Brill, you might be used to thinking functions contain instructions, and then it's up to me to construct the basic blocks. That's not true in the LLVM in-memory representation. That is, the infrastructure has already done the work of translating the file into this kind of object-y representation where this containment holds, where it's already organized things into basic blocks for you, and the instructions already point to each other in an SSA form. And that's one reason why LLVM can actually be easier to use than Brill, even though it's a much more complicated language, because it has all this existing tooling behind it that you get immediately as soon as you start writing your pass. To show you what all these objects look like, I want to start by just printing them out. So I'm going to go back to this small pass, and let's change it a little bit to actually print out, to sort of traverse from object to object in the representation of programs, and to print stuff out. So here I was previously just printing out the name of the function. A different thing you can do is print out functions themselves. So you can say if you want to print out the function f, including its entire text representation of its body, you can do this. As you can see, this has printed out the text representation of the main function. I got my message, and then it printed out the body. It serialized the function object as text so that I can look at it. It's going to be important when doing anything with these programs to traverse down that hierarchy of objects. That is, to open up the function and to look inside and process its basic blocks, and look inside those basic blocks and look at its instructions. So we can do that too. In fact, the modern C++ makes this pretty easy. All we have to do is write one of these for each loops using the auto keyword. So for example, we could say for every basic block b in the function f, do some stuff, and for every instruction I in that basic block, do some other stuff. So I'll do it this way. That is, I'll say I'm processing a basic block now. It's a little shorter than the way I wrote it before. And then inside here, I will print out every instruction as I process it. This will be super redundant, but it will help us see exactly what's going on with every level in that containment hierarchy of the program. Great. So you can see that the outer loop ran once, the outer loop ran once, and the inner loop ran once, and the inner loop ran 3 times, once for each instruction. In each case, just as a debugging tool, it can be helpful just to print out the thing you're looking at. You can print out basic blocks, you can print out functions, you can even print out modules if you ever get your hands on a module object. I encourage you to pause the video now and try writing this yourself in the pass that you have cloned from GitHub, and even try playing around with it and see if you can find other interesting things to do just by traversing the hierarchy of objects and printing stuff out. Next, I want to make this pass a tiny bit more interesting by doing 2 important things that you will always need to do in any interesting LLVM pass. That is, processing the program to look for patterns, and then transforming the program when you encounter that pattern. I'm going to do something very simple, which is just to process the program and find the first binary operator that occurs. That is like a plus or a minus or a divide or something, and replace it with a multiply. So super useful. That is, if I'm just adding together 2 numbers, and the first add I do will be changed with multiplying together those 2 numbers. So let's get started by trying to recognize the first binary operator. I'm going to delete all these printouts that I don't need anymore. And I'm going to keep this structure that loops over the function, then loops over the blocks, and to get to all the instructions in the block. I'm going to look for the first one that looks like a binary operator. Here's how to do that. You're going to want to use this utility called dynecast. It is a C++ template, and it's parameterized with a type. And it tries to do a cast to that type, and it tells you whether it succeeded. So we're going to try to cast I, or rather a pointer to I, to the instruction, to the class of instructions that represents binary operators. There's a class in LLVM that is called binary operator that you can find, as usual, in the documentation. Here it is. If you are ever curious about like other instructions, you can traverse the class hierarchy, but in any case, we just want to tell whether I happens to be of type binary operator. The way dynecast works is it produces a pointer of type binary operator star, so we can do auto star op and assign it to this, but it also can return a null pointer if the thing was not of that type. So every other instruction will produce null. Binary operators will produce the same pointer as the original thing, but now give you a thing of a different type. So we can wrap that in if, as is often done in C++, to tell whether this is tell whether this cast succeeded. That is, if we got a non-null pointer. So for now, I'm just going to try this out by just printing out op itself, only in the case that it is a binary operator. So instead of giving every instruction, we should now only get this one. I think that the program I've been compiling so far doesn't have any binary operators, so I'm just going to real quick check. Oh no, I need to import things. So this happens all the time too. You will note that we didn't add any includes when we started using a new class. At the top of the doxygen reference for most classes, it tells you what header you need to import in order to get the thing. So it's convenient to just copy and paste, and I hope this now works. It did. Okay, so I think that what I was saying before was that I think the source file doesn't have any binary operators, so I think this should print nothing, and it does. Okay, great. In order to avoid optimizations here, I'm going to put in standard arguments that you get from Unix, and I will just print out argc +5, just to have some sort of binary operator going on in here. That linter is mad at me that I didn't actually use argv, but that is intentional. Okay, so let's do it now. Great, awesome. So it printed out the only binary operator in this program, which is an add instruction. If you're curious what NSW does, that has to do with undefined behavior. It says no signed wrap. In any case, this is an add instruction that adds a register somewhere else in the IR and the constant 5 that it got from the source code. The next step, now that we have the instruction we want to replace, is to construct the new instruction, that is the multiply instruction that will replace the old instruction with. To do that, we're going to use a thing called the IR builder. An IR builder is a part of the LLVM library that's super, super useful for constructing instructions. So while it's technically possible to just use like C++ new or whatever to create a new instruction, it's going to be way better to call methods on the IR builder to create the instruction we want. As usual, it's useful just to copy the appropriate include out of the documentation, and we're going to construct an IR builder. So we'll need an instance of this IR builder class, and when you construct the builder, you need to tell it where you're going to be inserting instructions, and one convenient way to do that is to give it the existing instruction where you're going to insert, whose location you're going to use for inserting new instructions. So we need to construct this new multiply instruction. We will need to get the existing operands of whatever binary operation it is that we're replacing. So op is our old instruction. Instructions that use operands have the method getOperand. So we can say getOperand 0 to get the left-hand side. The type of this thing is some other value. Value is a really important class in LLVM. Values are the base class for a whole bunch of stuff in LLVM, including functions and instructions and even basic blocks. And they're basically anything that you can refer to from code. So the operand for the left-hand side operand for our binary operator might be another instruction, or it might be a constant value, or it might be a reference to a global, for example. all of these things are subclasses of value. So I'm going to take this left-hand side and put it into a value pointer. And I'll do the same thing for getOperand1, which is the right-hand side. Because as a binary operator, we know that there are exactly 2 operands. Now I want to create a multiply for these 2 operands. Just to be clear here, I'm throwing away the old instruction, and I'm going to construct a completely new instruction for the multiply. So I'll do that by again making a new value for the multiply, but now I'm going to ask the builder to create this for us. We're going to call a method on builder to create a multiply instruction. So returning to the documentation, IR builder inherits from this IR builder base thing, which is where all the interesting methods are. And there's a whole bunch of things called create blah. And one of the things is going to be create mul to create a new mul instruction, multiply instruction from the LLVM language reference. So I'm going to call the create mul method on this builder. And the things that it needs are just the 2 operands. So all I need to pass in are LHS and RHS. So regardless of what form those LHS and RHS are, they can be used as operands to the new multiply instruction. So now I have created this multiply instruction, and if we were to compile this, it would also be inserted into the new program. However, we need to replace the old instruction with the new one. The way to do this is to look for all the places that the old instruction was used, that is where its result was the operand to some other instruction, and then we'll replace those uses with uses of the new instruction. And the old instruction will still be there, but it will be dead code and eliminated when we compile the rest of the way. So here's how to do that. The old instruction op has this collection called uses, so we can iterate over this too. So I can say like auto, and I'll take a reference to every use, which is an object by itself in ops uses. We can then get the user, that is like who is actually using this thing. I'm feeling very divided apparently about which side of the space to put my stars and ands. Please forgive me. If u is a use, and we can ask it what its user is. A user is any value that has operands. So this is the superclass, for example, of binary operators, which have 2 operands. In any case, we can set the, we can take user, so that's, imagine this is some other instruction that is consuming the result of the old binary operator, and we'll do set operands. This is the opposite of get operand that you saw before. We'll need to give it an index, and then we'll need to give it the thing we want to replace, we want to set that operand to. And the thing we want to set it to is multiply. That is, we want to take the old operand, throw it away, and then insert our multiply in its place. Recall that this is totally following the SSA philosophy. That is to say that this multiply instruction is one and the same as the location that it puts its result in. That is, there's no distinction between like the instruction itself and the value the instruction produces. Those are both the same thing. So that's we need to figure out like which index of the operand we want to replace is. Fortunately, if we were to look up this use object in the LLVM documentation, there's a way to get that directly. So out of u, we can say get operand number, and that tells us exactly the thing we need in order to do this replacement. Okay, let's try building that. That worked. And let's try transforming it. Great. Okay, so I think we have now successfully replaced this old instruction with the new one. Oh wait, there's one thing I forgot, which is that now we need to return true. I'll just return true at this point here just to say that we're going to abort after replacing our first instruction. We return true to tell the rest of the pipeline that we have modified this function. Now let's check whether this pass is actually working. It's going to be a little bit funky. You can make this easier with an actual printf, but just bear with me for a second. So if we compile this thing normally with normal clang, this produces a program that we can execute. It doesn't print anything out. There's no printf in here, but we can ask what its return code is. And it should be the number of arguments that we gave to it plus 5. And I know this is a very contrived example, but again, please bear with me. So this got 1 argument, that's the name of the executable in the Unix convention, plus 5. This worked out great. Let's see, we can do like A, B, C or something. This should be 4 plus 5 is 9. I know how to do math. Great. Okay, awesome. So now let's recompile the same source code now using our pass. So this won't print anything out. I've taken the printout of the pass, but it will produce an updated version of the executable. And so this will be very exciting. if now this produces the number of operands, that is in this case 1, times 5 instead of added to 5. Let's see what it prints out. Well, that's to be expected, I suppose, because 1 times 5 is 5. But let's do a.out a, b, c. And indeed, that is 4 times 5 is 20, instead of 4 plus 5 is 9. I hope you've enjoyed this very ridiculous program and this transformation we have made, but I still think it's kind of exciting that we've taken a real program written in a real programming language, C, and transformed it to do our bidding. That is to do something that we absolutely didn't ask it to do in the original source code. It's a tremendous amount of power that we have as an LLVM pass. The next trick I want to show you is how to insert calls to a runtime library to do more interesting instrumentation. So far, we have just replaced one binary operator with another. But what if you want to do something complicated, something as complicated as printing to the screen, for example, when something happens inside the code? This can be useful if you're counting events or if you want to do extra logging while you're transforming a program. One way to do this is to manually generate the LLVM instructions to do the behavior you want as part of your pass. So you can use IR Builder to say, create me an instruction that makes a format string, create a call to printf, then put it all together and then ship off the call. You can do that, but it's super painful. An easier way to do that is just to insert calls to functions that you'll write yourself, and then combine the original program with your library of functions, and then execute that. So you get to write your instrumentation code in C instead of in funky C++ that generates LLVM instructions that then does what you want. So let's do that. What I'm going to do is, instead of replacing instructions, I no longer want to replace instructions, no longer want to generate multiplies. I'm not even going to need the left-hand side and right-hand side. I'm going to insert a call to a function that will just log the result of the first binary operator. In order to get a reference to the function that we're going to call, we're going to need to use the module that contains the function we're instrumenting. Remember, modules are containers that contain functions and globals and other stuff like that. We're going to need to insert a definition of the function that of the runtime function we're going to call. Even though this isn't going to contain any code, that's going to come later, we do need to have a declaration of the function available. So the way that works is we're going to take f, our function, and we can say get parent, and that is the module. Remember that modules contain functions, so this function's parent is a module. Modules have a method called get or insert function. There's several different forms of it, but there's an easy one where you give it the name of the function that you're going to call. Here, I'm just going to say that it's logop for log this binary operation, and we need to give it the return type. So that would be it's going to have a void return type. I'm going to fill in the arguments to this thing later. It's a little bit annoying, but we got to do get int32 tie. I'm going to make this take an integer as an argument. So the argument to these things you will find is something called an LLVM context. LLVM context is a really common object you often have to deal with, which sort of contains a bunch of general information about the environment surrounding all of the LLVM-based processing you're doing. There's a way to get a context from most stuff that you already have. We can get a context from f that we are processing. That's the argument to these get void types. That returns a type object that represents the void type. That is like the C void type, that is not returning anything at all. Got to return context there, and to pass in context there and there. Alrighty. So I think we now have the function we're going to call. Oh yeah, I'm going to, let's call that log func. The type of it doesn't matter. That is called the function callee. In any case, we now have a reference to the function, and we can use that to insert calls. So lower down here, where we are processing binary operations, remember we've already done our sort of pattern matching to make sure that we're processing the kind of code we want. In this case, the kind of code is binary operator. We just need to insert, instead of a multiply, now a call to this function. So by default, when we passed in op as the insertion point for this builder, that by default does it right before the instruction we passed in. We want to do this right after, so we can pass in the result of the binary operator. To do that, IR Builder has a method called setInsertPoint. So we can tell it which basic block we want, and we can tell it to increase the location within that basic block by saying get your current insert point, that is from what went before, to increase by 1 to go right after. So this sort of moves us right after right after op, where we want to consume the result. Now we need to do builder.createCall. So like everything else, it's like create something in Builder. This does the actual work of creating an instruction and inserting it into the basic block at the desired location. There are many different forms of create call. Again, look at the documentation. But one of them says you can give it the function you're trying to call and some arguments. The arguments you will want to construct separately. So an easy way to do this when you're making arguments to a create call function, to method call, is to use C++ syntax for initializing a ordinary C array. So this is that we can say a value pointer args, that is going to be an array of values. You can use this curly brace syntax to construct the initial value of the array. We have only one operand we want to feed in. That is the result of op. That is the output of doing the binary operator. Remember, in SSA, results are the same thing as functions. So we want to pass in the result of that instruction. We'll just pass in op itself. And now we have created the call to the runtime function. So let's try this out. Great. Just as expected, our instrumented code now contains a call to a function called logop that the linker can't find. And this is exactly what we expected. We have transformed the call to call a function, but we haven't actually written that function. Remember, the whole point of this was we wanted to be able to write our runtime functions like logop in C instead of generating the LLVM manually for it. So let's do that now. Let's do, I guess I'll just call it rtlib for the runtime library. So you'll think of this as kind of like part of the pass, but it's being compiled separately and then linked in with the programs you want to instrument. So remember that we're going to want to define the signature of this function to match the signature we used with the getter insert function from the pass. So we made a function called logop that had a void return type and had an argument that was just a single integer. So we got to do something like this, and I'll just do the easiest possible thing I can think of, which is to say that just tell it that we have now computed this binary operation, and we'll pass in I. And of course, I will need to include the IO header for C. And the nice thing about this is that you don't have to worry about how complex this program is because you'll never be processing it with your pass. This is just something that you get to write on the side, and then the interface between your pass and the runtime library are the signatures of these functions that you might call. So now we need to put it all together. That is that we need to compile our runtime library, compile the code to be instrumented, smash it together with the linker, and then run that. So first things first, we just need to compile the runtime library. And the important thing about this is that you don't have to compile it with your instrumented version of Clang. You can use like whatever compiler you like. I'll just use the default C compiler in my system referred to by CC. So to get an object file out of this, I'll use -c. That should give me rtlib.o. Great, cool. Just normal C compilation stuff, no magic, no LLVM magic going on here at all. Now we can use Clang with our magic options to compile C, to compile a.c, and I will use -c again, and we should get a.o. Awesome. So all we have to do now is link this stuff together, so we can use cc again to do that, to compile rtlib.o and the instrumented a.o, and say that we're going to do this to executable called exe. I have no idea what that message means. I hope it's okay. In any case, it worked. It told us that it did the addition. Remember that this is just taking the number of arguments, 1, and adding 5 to it. And then this is previously never printed anything out, but now it does print something out because it called our runtime library, which does the call to printf. If you make something interesting with LLVM for your task, I hope that you will find this technique useful to be able to write runtime behaviors that you want to instrument programs with, but not have to write them in LLVM instructions, to write them in actual C code. We have only really just scratched the surface. LLVM is an enormous library with a whole bunch of built-in optimizations and analyses that you can use to build amazing things that could process C-like programs. But now you have the basic tools to begin exploring. You have all you need to start building more and more interesting passes that operate on LLVM programs. For your task, you just have to cook up some interesting idea that's completely open-ended and implement an LLVM pass to do it. Please confine your ambitions to writing a pass of some sort. There's many other things you could build with the LLVM infrastructure, but just to keep things scoped, build something that can be phrased as an LLVM pass. Have a great time, and please ask lots of questions as you get familiar with the LLVM infrastructure.